previous example, we went through how to calculate the soil pressure and forces on the back of the wall. It looked like a bunch of chicken scratch like this. We're going to pick up where we left off. I'm going to redo this part really quickly with less explanation. So if you feel like you're at a loss, go back to that other video. So we've got a retaining wall. This is a solid concrete block. It's 15 by 20. It's embedded 5 feet. And the groundwater table is at that location. It's retaining soil that's backfilled at an angle of 10 degrees. And the last time we went through the calculations for getting the pressure, and we talked about how the water table's on both sides of the wall. And so to be able to do the calculations, the first thing we need to do is get the active pressure K. So K active is cosine of beta minus the square root cosine squared beta. This is beta. And we just change the sign for the denominator. We need to get phi for the soil. So this soil phi is 40 degrees. And we need to know the unit weight of the soil. That's 110. And so if we do the calculations, we get a K of 0.228. And so to be able to do the calculations, because there's a change in slope in the pressure distribution at the location of the water table, let's call out this as point B, and this will be point T. So we need to calculate the stress at B, the vertical stress. So if we do that calculation, and then we keep in mind that our pressure distribution at the back of the wall, so I'm drawing this face now, it's going to look something kind of like this. So Rankine's theory says that the resultants are inclined at the same angle as beta. And so beta is 10 degrees, so we want to keep that in mind when we're drawing this thing. That's why it's inclined. It's a little bit confusing. I had some questions about that. So this is B, this is T, or 15 feet and 20 feet. So we'll take our stresses that we calculated above, and we will multiply them by Ka to get the stress here and here, if we're interested in that. And then what we're going to do is we're going to break this thing into the corresponding resultant forces. So the pressure distribution from the triangle on top, let's call this area 1, is easy enough to get. And then the resultant force for this section, area 2, is also fairly easy to get, and same for 3, but we've got to remember that we need to break them into separate sections. So what we end up with is a resultant force, let's call that R1, and it's 2/3 of the way down of 15 feet. This is going to come back here in a second. Maybe we'll make another drawing. And then we'll have a resultant force that happens halfway down from 15 to 20 feet. That's going to be R2. And then finally there's an R3 that just corresponds with the last bit of the triangle. So let's calculate those. So R1, the calculation is going to be the area of a triangle. So 1/2 times the horizontal, or the active pressure. It's not horizontal pressure. So we're going to take the vertical pressure and multiply it by Ka. That's 1650. And then that gets multiplied by the height of this section, right? So 15 feet. And this is going to be pounds per foot of wall. So R2 is rectangular, so we don't get the 1/2 component. We're just calculating the area of these corresponding sections that are called out as 1 or 2. So calculating the area of this section right there. So it's the active pressure times its height, so base times height. So 5 feet is the 20 minus 15 to get 5 feet. And then the last one, we just need the base for this triangle is just this dimension right here. So that base is 1/2 for the area of the triangle. And then the base is going to be 0.228. That's the active pressure. And then the difference in vertical pressure. So and then it's going to be multiplied by its height of 5 feet. So that gives us 135 pounds per foot. Okay, so these are all inclined, and when we're doing our factor safety analysis, we've got to take those out and turn them into components in the vertical or in the horizontal direction. So let's redraw these resultants by themselves along a back face of a wall. So here's 0, 15 feet, and 20 feet. R1 is going to be inclined 10 degrees, and it's going to be at the location, let's see, let's call this that dimension is 2/3 of 15 feet, right? So that's the location of the centroid of a triangle, is 2/3 of the way down. And then R2 it was a rectangular shape, so it's going to be halfway between 15 and 20. So its dimension is going to be 1/2 of 5 feet. And then R3 it's going to be one, because it's a rectangle or triangular shape too. It's going to be 1/3 of the way up 5 feet. So that's its moment arm that we'll need to. So we'll need to use all of those moment arms. And so now what we need to do is we need to get let's get the horizontal component of each of these. So let's call this horizontal component P1, and we should have been calling these over B, and the over B symbolizes that this is a per unit length calculation. So we're going to have answers in terms of pounds per foot. So the little b indicates that it's per foot. And we're going to also get P2 over B, and then finally P3 over B. So we're just going to use a sine rule, so sine and cosine. We're going to take those forces multiplied by the cosine of the angle that it's inclined, which is 10 degrees. I think you're getting the idea. Okay, so we've got that taken care of. Now we need to get the same thing for the vertical component. So we need to get V1 over B and R1. Sorry, that's that's V2 over B. And then V3 over B. And we're going to need to add these up. So if we sum those up, we get 840 pounds per foot. And those are all acting right at the back side of that wall face. So all of those vertical forces are sort of acting along the back face of this wall. We need to know the weight of the wall. So we've got a big chunk of concrete right here. We're going to calculate the weight of that using a unit weight of concrete of 150. And then we need to reduce for the buoyant force of the water. So that's the weight. This calculation that's shown here is just the weight of the footing, but there's also a buoyant force. So we get 40 kibs. And we're going to need to get the frictional component along the base of the wall. So in a previous example or video, I set up how the factor safety thing works. So we're interested in the frictional component along the bottom of that. That'll be a resisting force of sliding. So the frictional force, it's just the sum of the vertical forces. In this case, it's going to be multiplied by the tangent of 2/3 of the friction angle. And so the sum of the vertical forces in this case are the weight of the footing and then also the vertical summation that we calculated from the soil, right? So this is the soil force, and we're going to add that in here. Friction angle is 40 degrees. So the frictional resistance to sliding is 20 kips. Okay, so now we're ready to do our factor of safety for sliding. And so that is, we need to know the driving forces. And that's going to be all of those soil forces that we added together. So, and that's just in the horizontal direction, remember. So there's the driving forces. So our factor of safety for sliding is the resisting over the driving. And the resisting was that frictional component. Or 4.3. So our factor of safety is 4.3 in sliding. Now we didn't count any passive pressure in this case. If that value of 4.3 was too low, maybe we would try and go back and do some passive pressure calculations and see if we could get closer to an acceptable factor of safety, something like 1.5 or greater. Let's do overturning. So in this case, we need to know the resisting and the driving moments. And so first of all, so if this is our object, this is our free body diagram, we're going to do overturning about this point at the toe. And so we need to know what are these moment arms in each of these directions, depending on which direction the force corresponds with. So the first resisting force is the weight of the footing, and that happens at the centroid of the footing. So that's 4320. And so its moment arm is going to be the dimension 15/2. And then we've got all the frictional resistance at the back of the footing. So that was 840 times 15 feet. Okay, and so if we do that calculation, it's 315,000 pound-feet of moment per foot of wall. So then the driving forces, sorry, these are driving moments, are going to be each of those resultants that we calculated times their moment arm above the bottom, or above the toe. So the first one, 2780, is because we've got first, so the first, I think it might be helpful to redraw this figure. Let me redraw that. So here's 15 feet, here's 20 feet from the top. But another way to think about this would be to say, here's our point of rotation, so that's 0, and then 5 feet, and then at the very top it'd be 20 feet. So that's a moment arm. And our first driving force that we're calculating is right here, 1/3 of the way down from the top to 5. So that is 5 feet plus 1/3 of 15. Our next driving force, so that one was, that was P1. So now we're going to come up with R1, or sorry, P, that's P2. And so P2 was the rectangle. And so P2 is 1852. And the rectangle was just from 0 to 5 feet. So that's half of 5 feet for its moment arm. And then the last force that we calculated was due to that last little wedge of a triangle at the end. So that was P3. And P3 was 133, and its moment arm was 1/3 of 5 feet. So if we do all those calculations, we end up with 32,652 pound-feet per foot of wall. So then our factor of safety is 9.6. So here's one example of a factor safety approach for sliding and for overturning. So it's not too bad. It's basically a statics problem. The trick is getting those forces and keeping track of where the forces land. So what are their moment arms? What are the directions that they're working? Keeping in mind that the vertical component of the driving force is actually a resisting moment. And you need to include that in calculating your friction component of force along the base of the wall. So we'll continue from here to do a few more examples, and then we'll look at a few different types of retaining walls and learn things about mechanically stabilized and sheet pile walls.